Alright, so in this video, we're going to be discussing the shapes of molecules, alright? And then once you've determined the shapes, we're going to also um, see if a molecule is polar or non-polar, alright? Sometimes there are molecules which have polar bonds, but the molecule itself is non-polar, even though it has polar bonds, alright? And we'll see why that happens, okay? All right, coming back to shape, you see here, this is methane, carbon attached to 4 hydrogens with 4 single covalent bonds. Now, when you write this Lewis structure on paper, it comes out looking like this, kind of flat. But that's not how the 3D shape of this molecule methane is. It's more closer to what you see here with this ball and stick model, all right? So you have the central atom, which is carbon here, and then surrounding it are the 4 hydrogens attached to it with single covalent bonds, okay? And so you have one bond up on top, one bond to the side like so, and then one bond which is behind the carbon, all right? So behind, like into the paper, behind the paper rather, and then one coming forward out of the plane of the paper, all right? Sometimes in order to give it more justice, rather than writing it like this, they use this method of drawing the formula for methane, where you have this wedged line showing the hydrogen that comes out in the front, and then the hydrogen in the back with a dash line, okay? Um, the other thing to note is what the shape is like. So the shape is kind of like this pyramid type of shape, and that is referred to as tetrahedral. So the shape is tetrahedral shape. Now, in terms of determining shape, we use this term called as electron group geometry. Geometry is meaning the best shape possible. Now, what is the best shape possible for um, 4 single covalent bonds surrounding the central atom? So the shape is always with respect to the central atom, all right? Not the surrounding atoms, but just the central atom, all right? So that's the pivot point. Now, each bond is made up of 2 electrons. So if they're too close, there's going to be a lot of electron repulsions, all right? So you want these bonds to be as far apart as possible to minimize those electron repulsions. So that best shape that is possible, or the best geometry that is possible to minimize repulsion when you have 4 single covalent bonds, is the tetrahedral shape. The bond angle, that is the angle here, all right, between these two bonds, is 109 degrees, all right? So 4 single bonds, tetrahedral shape, bond angle 109 degrees. So this is based on the VSEPR. The acronym used is VSEPR theory. And that's the abbreviated form of valence shell electron pair repulsion theory, okay? So this theory states that these electron groups around the central atom have to be as far apart as possible in order to minimize electron pair repulsions, okay? So that shape of the molecule is determined by how many of those bonds are around the central atom. So it's always with respect to the central atom. All right, so here we see a molecule of carbon dioxide, okay? Now, in this VSEPR theory, you treat a double bond as one electron group, all right? So this double bond here would be one electron group, and this double bond here would be another electron group. So carbon, the central atom in CO2, has 2 electron groups, okay? So according to Vesper, if you have one or just two electron groups, then the best geometry is linear. You have to have those groups as far apart from each other as possible, and that's linear 180-degree angle. All right. So the shape around the central atom, carbon, is linear. Now, if around the central atom, like you see here in formaldehyde, which has a molecular formula of H2CO3, and you have the two hydrogens. This is a mistake. This is H2CO. This shouldn't be. H2CO3 is carbonic acid, right? So this is a typo here. Ignore this 3. It is H2CO. All right, so in H2CO, you see the central carbon atom, and how many electron groups do you see around it? This is one electron group, this is another, and this is the third electron group. So 3 electron groups around the central atom. And to minimize repulsion, the best possible shape is trigonal planar, all right, like a triangle. And therefore, just like a triangle, the bond angle is 120 degrees, all right? And planar is all of these, unlike methane where you have one bond going behind and one coming forward, all of these bonds are in the same plane, so it's planar, all right? So that's the shape for 3 electron groups. So what happens if you do have 3 electron groups, but one of them is a lone pair, as in SO2? So you have one electron group, the lone pair is the second electron group, and the single bond is another electron group. So 3 electron groups, 2 of them are part of the bonded electron groups, but one is a lone pair, all right? So you have 2 of them part of the bonding electron groups, and then one lone pair, all right? Now lone pairs, because there's nothing to anchor them, like these bonded electron pairs are anchored between the 2 atoms making up those bonds, all right? Whereas the lone pairs have nothing to anchor them down or fix them in space. So they're very diffuse. They take up a lot of space. And when they do, there is electron repulsions between the lone pairs and those bonded electron pairs, which means that those bonded electron pairs get pushed down, all right, or they get pushed in closer, all right, because this lone pair is occupying so much of space and pushing them inward, all right. So instead of that trigonal planar, the nice triangular shape, it becomes like an inverted V, a bent shape, all right. Now, the bond angle is not quite 120, it's a little less than 120, all right? So, in sulfur dioxide with 3 electron groups, 2 bonded pairs, and 1 lone pair, it's called a bent shape with a bond angle of less than 120, but for the purposes of this book, we can take it to be 120 degrees. Okay. So 4 electron groups, that was tetrahedral methane. Okay, now in ammonia, if you look here, it has the 3 bonds and 1 lone pair. So that means it's 4 electron groups around the central atom of nitrogen, all right? But one is a lone pair. Again, remember, lone pair occupies a lot of space, so it pushes down on these bonded pairs of electrons, all right? So they get pushed in. So again, instead of the nice tetrahedral shape, this becomes like a true pyramidal shape, all right? The geometry looks more like a pyramid, all right? So this is called as a trigonal pyramidal shape, okay? Now, the bond angle is not quite 109, it's less, it's around 107 degrees, all right? Again, for the purposes of the book, we can assume it to be 109, all right? It's slightly less. Okay, so in the ball and stick model, you would represent it like this, like a pyramid type of shape. Okay, so that is ammonia. Now in water, you have two bonds and then the two lone pairs. So again, around oxygen, you have 1, 2, 3, and 4 electron groups. However, 2 are bonds and 2 are lone pairs, all right? So again, that pushing down the space occupied by the lone pairs is going to be even more, and they push down even more on the bonded electron pairs. So again, it becomes like a bent and inverted V kind of shape, all right? So this is also referred to as a bent shape in water, all right? And the bond angle is, of course, less than 109, but it's around 105. But again, for the purposes of this book, we'll take it to be 109, okay? So to summarize, if it is 1 or 2 electron groups around the central atom, then the shape is linear, all right? The two bonded atoms, remember, even a double bond is considered to be one electron group, all right? So there's no lone pairs, it's 180 degrees. If you have 3 electron groups, that means 3 bonds, right? No lone pairs, then it's trigonal planar 120 degrees angle, all right? Formic acid, H2CO is an example of that. If it is 3 electron groups, it should be trigonal planar according to the electron group geometry. However, 2 of them are bonds and 1 is a lone pair. So its bond angle, again, should be less than 120, and the shape, molecular shape, is not the same as the electron group geometry. It's bent, okay? And the example is SO2. If it is 4 electron groups, the electron group geometry is tetrahedral, 4 bonds, no lone pairs, the bond angle 109, and the shape is also the same, tetrahedral, all right? Now, if you have 4 electron groups, so the electron group geometry is tetrahedral, however, there are 3 bonds, 1 lone pair. So that shape is trigonal pyramidal, okay? Again, 4 electron groups, electron group geometry is tetrahedral, but there are 2 bonds, 2 lone pairs, so the shape is bent. So how do you determine this molecular shape? You're first going to draw the Lewis structure. Without the Lewis structure, you don't know how many of these electron pairs are bonds or lone pairs, all right? So once you have determined how many bonds and how many lone pairs are around the central atom, then you are going to follow that table that we went through to then apply those rules of Vesper and then determine what the shape of that molecule is. So here is an example. You have H2S, hydrogen sulfide. So if you look at the Lewis structure, there are 2 bonds and 2 lone pairs around sulfur, the central atom, right? So electron group geometry is 4, tetrahedral. However, the shape is not going to be tetrahedral. It's going to be bent, right? So it's going to be bent. All right, so you're going to apply Vesper to PF3, H2O, and CCl4, all right? PF3 is going to be just like ammonia, like NH3. It's going to be pyramidal. H2O, we already did, it's bent. CCl4 is going to be like CH4, tetrahedral. Okay, so determine the Lewis structure, and once you do that, then it's easy to then apply the Vesper theory. All right, and we'll stop.